This tutorial will illustrate how to model staggered trusses using etabs. We will model a 6-story building with staggered trusses in the transverse direction. We will take advantage of the staggered trusses to limit our typical story height to 10 feet, and we will use 8-inch precast planks to span 30 feet between trusses. Chord members will be limited to W10s, and diagonals will be constructed from hollow structural sections. Start the model by defining the basic geometry. 5 grid lines in the X direction, 2 in the Y, with spacing of 30 feet and 65 feet. Set the number of stories to 6 and the typical floor height to 10 feet. The first floor is 15 feet. Select the staggered truss template and note that the default Verndale panel width is 7 feet, which we will not change. Let the number of default panels remain at 3, as well as leaving the truss at the top of the first bay. We will also let most of the default auto-select section stand for the cords and webs, except for the knee brace, which we will switch to the cord auto-select list. We will alter the web and plank properties later to meet the model requirements. The model geometry has now been generated. For a clearer view of the staggered truss framing, switch to an elevation view and turn off the secondary grid lines. Note along grid line A that the trusses start at the top level as specified in the template. Note also the Verndale openings in each of the trusses. If we toggle to the next elevation along grid line B, we see that the top story does not have a truss, but rather is supported by posts, while the first floor is hung from hangers. Switch to the plan view and notice that the column orientation is such that the strong axis is parallel to the truss direction for the longitudinal moment frame. Next, click on the Define Frame sections to modify the Web Auto-Select list. The auto-select list specified for the webs was TR Web 10, which consists of a list of W10s. However, for our trusses, we wish to limit the webs to hollow structural sections with a minimum dimension of no more than 6 inches. So remove the W10s and select HSS 10 by 6 sections. The W10 list for the cords is appropriate, so we will not change those elements. Next, click on the Define Slab sections and select Plank 1. We will change the thickness to 8 inches and make sure that the one-way load distribution is selected. A check of the modifiers shows that F11 and F22 are set to 0.01. This will prohibit the diaphragms from acting as flanges for the trusses by not allowing them to carry axial forces. Next, make the plan view active and select all stories. Click on the Create Walls and Region button to add non-structural and go to the Select by Frame Sections command and click on the Truss Cord W10 Auto Select list. This will select all of the cord members. Go to the Design, Steel Frame Design, Revise Overrides command, and set the end brace length ratio in the minor direction to a small number to represent the lateral support offered by the planks. Go back to the Design menu and start the design. The design is complete, but this note indicates that a number of the sections selected in the design phase differ from those used in the analysis. So typically we would iterate through the analysis and design at least one more cycle, or until the sections matched. Next, display the design sections on the elevation. If we window in, we see the W10s were used for the cords and HSS 10x6s for the webs, which is as we specified. We can also view stress ratios on this view. And then toggle up to the next elevations to review the results for the other frames. Next, switch the elevation view to that along line 1 and display the deformed shape for the earthquake load in the X direction. A right-click at any point on the deformed shape diagram will bring up a box showing the displacements. If we select a point at the roof, in this case point 9, we see that the displacement in the X or earthquake direction is 4.34 inches. Comparing this to a drift target of 0.005 times the building height, we get a displacement of 3.9 inches. So our current displacement is slightly larger. However, etabs provides a tool which helps you to match any number of target displacements. And in this case, we will set one target by going to the Design, Steel Frame Design, Set Lateral Displacement Targets command. And for point 9 at the roof, input a value of 3.9 inches for max displacement, and then click on Modify. The default displacement displayed was based on a drift of 0.0025. We are now ready to rerun the design, where the program will optimize the member selection based on energy principles in an attempt to match the requested target displacement. The redesign is complete, and now we are ready to rerun the analysis with the updated sections. Once the analysis finishes, switch to the elevation view and again show the deformed shape for the earthquake load. A right-click on point 9 at the roof now shows that the lateral displacement has been reduced to 3.29 inches, down significantly from the original 4.34 inches and under our target. Next, view the forces in the concrete deck by switching to a plan view and going to the Display, Show Member Forces, Shell Forces command, and select the wind load in the Fmax component. You may toggle down the building to see how the forces change. And a right-click in any region will bring up an area diagram where you can move the cursor around for specific values. A final step should always be to verify that the design members have passed the stress check. This is done by going to the Design, Steel Frame Design, Verify All Members Passed command. This concludes this tutorial.